All right, welcome to class. This is CS4510. I think it's L16A, Cook-Levin theorem. Today is basically, we're really talking both before and after the break about one class, which is NP. And we have some familiarity with NP because we've talked about NP in the context of NP completeness reductions in 3510. So just to give you a quick reminder, if A and B are any kinds of languages, we may say that A is polynomial time reducible to B, and we write this little symbol to mean there exists a polytime computable function f such that w is in A if and only if f of w is in B. And the way to think of every reduction in this form, at least, is a picture where it maps good to good and bad to bad, but perhaps not so in any fancy or subjective, injective way, right? Something like this is A and this is not A, this is B and this is not B, right? Maybe this might be coming back to us. And if you recall, a polytime reduction, we thoroughly investigated this in 3510, but just kind of a refresher. It's basically a complexity version of the mapping reduction or the many-one reduction that we did when we were in the theory of undecidability. The same way we were able to show some problems were decidable or undecidable by a reduction, we can use this polytime reduction to show some problems tractable or untractable. So primarily, if A is polytime reducible to B and B is a problem that is in P, then that implies that A is a problem that is in P as well, right? Here's the proof. Let F be polytime computable so we know that W is in A if and only if F of W is in B by the definition of our reduction. Let alg for B be a polytime algorithm for for B. We give a polytime algorithm for A. Here's how it works. Alg for A, on input W is going to first compute f of W, and then it's going to return alg for B on f of W. Why does this work? Well, we want to determine if a string is in A or not in A. Alg for A is supposed to be a decider for A. So it wants to first off be able to distinguish things that are supposed to be in A and things that are not supposed to be in A, and it wants to be able to do so efficiently in polynomial time. So what it's going to do is first compute the reduction and it can determine if something is in B or not in B efficiently. So it computes the reduction efficiently and then it determines if it's in B or not in B efficiently. And if it was in B, you know it came from something good in A, and if it was not in B, you know it came from something bad in A. So whatever that'll do will tell you the answer, right? This line takes polynomial time. This line takes polynomial time. It's probably a polynomial amount of like register copying, whatever, who cares? This is certainly a polynomial time algorithm, and that's sufficient for us to prove that A is in P, right? If you think about it, this is not so different than the proof we've done before when we said that if B is decidable, then A is decidable. In some sense, P is just the efficiently decidable. So if B is efficiently decidable and the reduction is also efficient, then A is efficiently decidable. That's kind of all it's really saying here, right? It's really the same proof we've done before when we said let there be a decider for B, or even a recognizer for B. There's a recognizer for A, right? Take this statement, though, and we take the contrapositive of it. What is the contrapositive of B and P implies A and P?
A not in P implies B not in P?
Correct. Exactly. So if we have a reduction from A to B, the way you should think of it is if A is not efficiently solvable, then neither is B. So in some sense, B is harder than A, Or if you think this version of it, A is easier than B. So when you think of it, B is harder than A, and A is easier than B. That's the best way to think of it, right? Now, showing such a implication is actually quite easy, because all you have to do is give a reduction. So you can show this reduction, you can show this implication 1,000 times. What's difficult is showing the hypothesis of this implication, right? P implies Q is easy to demonstrate. P is not easy to demonstrate. How do you prove a problem is not in P? That's might help you do something about P versus NP, and there's very few problems that we know this for, right? To give you the picture about why we care, you could think about the relationship between P and NP as this kind of picture. Right? The definition of a language, let's say B is NP complete when is true. Does anyone remember? This is a trivia question.
In NP and it's NP hard.
Yes, correct. B is in NP, and B is NP hard. But what does that mean? You remember?
It can be reduced from another NP hard problem.
Correct. Now there's two practical definitions. There's a practical definition, and then there's the technical definition, which is basically the entire point of today's lecture. So you choose some other problem. The formal definition is that for all A in NP, there's a polynomial time reduction from A to B, right? So the way to think about this is, if B is in NP, it's at least not in some larger class. 3510 you wouldn't care about this, but 4510 we do. There's about 17 other classes here you can name. There's B space, exponential time. There's a countably infinite hierarchy of classes here. But if it's in NP, it's at least this easy, okay? It's somewhere here. You can at least verify a solution to it. That's not true of every problem, by the way. Chess is a good example. We don't really know how to efficiently verify chess. In the sense that, let's say you're given a board, can you determine if who's winning, right? You can do an exponential search on this thing to find out who might be at an advantageous position, but you can't really convince someone of that answer. They would have to repeat the whole search intuitively. Can't prove it, but that's what we're pretty sure of, that generalized chess is not in NP. There are some other problems that we're convinced are not in NP as well. SAT complement, for example, right? So it's at least that easy. Now, when you prove that it's harder than all of NP, what that really means is that you do this. It's not really a class, but this is the problems that are NP hard, right? So somehow the problem is in NP, but harder than all of NP. And that's where the term completeness comes from. It's at the tip of NP. It's in NP, but it's still harder than everything in NP. That's why we call it NP hard, that's why we call it NP complete. It is a problem in NP that is of the hardest problems in NP. That's what it means to be NP complete, right? Now, in practical definitions, when you actually prove a reduction, you don't show for all A and NP there's a reduction from A to B, right? What you actually do is show a specific reduction. In fact, the reduction tree, if you recall, So the first real problem we talked about in 3510 was SAT. And then from SAT, we went to 3-SAT. Actually, I'll do it like this. We went to 3-SAT. And then from 3-SAT, we went everywhere. We went to circuit SAT. We went to independent set. Independent set, we went to clique. We went to, from independent set, we went to vertex cover. Independent set, we can go to scheduling. Clique, we can go to subgraph isomorphism. From 3-SAT, we can also go to, subset sum. And then from subset sum, we can go to knapsack. From subset sum, we can also go to this puzzle game. Some of this you don't remember at all, but I'm covering some other stuff in 3510 this semester. From 3-SAT, we can also go to 3-coloring. And then from 3-coloring, we can go to n-coloring. Am I forgetting anything? 3-SAT, we can also go to Mario. Mario is NP hard. What else? Anyone remember any other NP complete problems? Okay. Essentially, everything kind of follows from 3-SAT. And the way you do this web of reductions is you go from SAT to everything. Now, here's the thing, though. All these problems, the NP hardness, by the way, the polynomial time reduction is transitive, right? So if you can go A to B and B to C, you can go A to C. So in some sense, for example, clique is hard, because you can reduce from independent set to clique, and you can go from 3 sat to clique. So we know clique is at least harder than 3 sat, right? But why are any of these hard? Showing the reduction is not sufficient. In order to prove NP hardness, what you have to do is prove for all A in NP, there's a polynomial time reduction from A to sat. For all A. That's what Cook-Levin is. Cook-Levin is this for all part. This is Cook-Levin. And this was a piece that was missing in 3510. In 3510, you just assume that sat is hard. And intuitively, I mean, it sounds hard, right? So all these problems are harder than sat. Today, we're going to prove that there is a reduction from every problem in NP to sat. That's what we'll prove today. Questions on that so far? I can give you one more quick explanation on why we care about NP completeness. So there are something like 60,000 NP complete problems. I'd make that number gets bigger every time I say it. 70,000. Let's see. Let's do that one. So there's this book from 1979. It's a bit outdated now, but is it really? Some of this theory is timeless, and it's called Computers and Intractability by Gary and Johnson. And they detail, in the beginning, they try to explain like why should people care about NP completeness, and they use this little cartoon image. So basically, there's this guy, and he works in industry back when Bell Labs used to exist. These guys were Bell Labs guys, and Bell Labs, these guys want to actually solve problems. Kruskal invented Kruskal's algorithm for minimum spanning trees because he wanted to minimize the amount of wire that AT&T had to lay down. So some research scientist is there. He's been given a problem called the Bandersnatch problem, which kind of sounds like knapsack if I printed the previous page. So you can't solve the problem. So you go to your boss and you say, I can't find an efficient algorithm. I guess I'm just too dumb, right? You don't want to do that for obvious reasons. So instead, you try to prove something intractable about the problem, perhaps even undecidable. So you work on the problem, maybe you try to prove it's undecidable. Maybe you try to prove that there's no polynomial time algorithm. As we have said, that's kind of difficult. To avoid serious damage to your position within the company, it would be much better if you could prove that the Bandersnatch problem is inherently intractable, that no algorithm could possibly solve it quickly. You can then stride confidently into the boss's office and proclaim, I can't find an efficient algorithm because no such algorithm is possible, right? So there are only like 3 problems I can think of off the top of my head that are proven to not be in P. But those are also not proven to be in NP. Otherwise that would prove P does not equal NP, right? So there are some problems that we know are not in P, and they're something much larger, but we have no way to verify them. So like that doesn't prove anything about P versus NP. But there's only 3 such problems. Meanwhile, there's 10,000 NP complete problems. And so it's very difficult in practice to prove something to be inherently intractable in the sense that it might be undecidable. So instead, what you do is you prove the problem to be NP complete in the sense that it's as hard as all these other problems. And so you stride into your boss's office and you say, I can't find an efficient algorithm, but neither can all these famous people. So in some sense, when you prove a problem to be NP complete, it enters a sort of suicide pact with 10,000 other problems, okay? And each of those problems has experts who worked on that problem for their whole career and were unable to solve it, right? So if you were to find an efficient algorithm, you would find an efficient algorithm. If you were to find an efficient algorithm for one NP complete problem, you would be able to find an efficient algorithm for all of them, right? If you were to prove any NP complete problem was not in P, then you could prove that all of them are not in P. Why is that true? Let me see if we can show you the picture, right? So this is actually, this web of reduction is actually the suicide pact, right? So for example, let's suppose subgraph isomorphism is polynomial time, okay? You can then compute the reduction from sat to 3 sat to independent sat to clique to subgraph isomorphism, but because subgraph isomorphism can be put in P, then so can A, for any A in NP. And we proved that if B is in P, and there's a reduction from A to B, then A is in P, right? So a polynomial time algorithm for subgraph isomorphism proves all of NP can be put in P. So P equals NP, right? Similarly, because you proved all these problems except Mario we didn't actually prove was in NP, but all these other problems, because they're proven to be in NP, there's a reduction from them to sat. So all those other problems also go over here. and then you go to SAT to whatever that efficient algorithm is. So any efficient algorithm for any of them is an efficient algorithm for all of them. Similarly, if you could prove any of them are not efficient, then all of them are not efficient, right? It's, that's the way they join themselves. Right, any questions so far? Okay, let me give you the formal definition of what SAT is, just so we recall ourselves. A SAT consists of problems that are a logical formula, right? So there's a few parts. First off, we have variables. These are of the form x1 to xl. And these are assigned, in assignments to our logical formula, these are assigned to 0 or 1, a true or a false, right? Then we have literals, and a literal is x1 to xl, or not x1 to not xl, right? So a literal is a variable or its negation. A clause is an or of literals. For example, x1 or x7 or x2, something like this, right? And then a CNF, conjunctive normal form, not Chomsky normal form, conjunctive normal form is an and of ors. Something like that, right? Conjunctive normal form is thought to be very hard, and many practical problems appear to express themselves as a kind of conjunctive normal form. It's a very natural problem, and it's interesting that NP is an entire class of problems, but the entire class of problems can be reduced to this simple problem. That's kind of it. What is SAT? SAT is the problem of you're given encodings of formula such that phi is satisfiable. And a formula is said to be satisfiable if there exists a satisfying assignment. Can you plug in variables into that such that they have the formula output of 1, right? So let me give you an example. Let this be a CNF that takes as input 2n variables. Let's say x1 or y1 not, and x1 not or y1, and xn or yn not, and let's say xn not or yn. Okay. This is just a CNF. What satisfying assignments are there for the CNF?
Any assignment?
Any assignments? Consider, so when you have a CNF to be satisfied, every clause must be satisfied, right? So could we make one clause unsatisfiable? Try 0, 1. Yeah, that would make it unsatisfiable.
Either x1 or y1 has to be true.
Correct.
So for each...
Well, actually, what if they're both 0? If they're both 0, it would work too. This is a good exercise, I think.
So they both can't be 0.
Both could be 0. x1.
We just said that they can.
Yeah. The point of this exercise is that CNFs are surprisingly powerful. Like, this has a very simple answer about what kind of things satisfy it, but it's a bit surprising. If you forget the n for a second, just to focus on these first two clauses.
X and Y are tied as the same value?
Yes, x must equal y. If x is 1, y must be 1. If x is 0, y must be 0. So if you generalize for n, what possible satisfying assignments does this have?
X is equal to y?
Yeah, this is a CNF for string equality. You can do equality in CNFs. You can do everything in CNFs, it turns out. That's kind of what we're going to prove. We'll be able to do every single problem in CNFs. I mean, like, it's surprisingly simple and or not, but that's basically what we're gonna do. Like, every single thing, that's the reason SAT is such like a universal problem, even though it's just made of ands and ors, is that, ands, ors, and nots, is that you can basically do anything in it. And it turns out all of NP can be reduced to SAT, as we'll see, right? So we need to prove, the problem with this first reduction is that in 3510 you did problem to problem, right? You did 3 SAT to independent set. You go from one problem to one problem. We need to go somehow from all A in NP, every single problem we can reduce from A to SAT. How are we gonna reduce from all problems? That's the first challenge we need to meet, right? All problems can be reduced to SAT. So what we're gonna do first is take care of this for all in a special shim. We'll reduce from all A to B to some specific B, and then we'll reduce from B to SAT. That B will take care of the for all part for us, as we'll see. Now, what is B? B, you're not gonna believe this. When does a language accept? When is a language in NP? The definition of NP is what again? Yeah.
If there's a verifier that can be run in polynomial time.
Yes, in fact, we have two definitions. The verifier definition or the non-deterministic definition. I only rehearsed the non-deterministic definition, so we're gonna go with that one, but every time we mention one, I'll make a comment about the other, okay? B is just gonna be like, we know A is an NP when there's a non-deterministic machine or a verifier, right? So let's just encode the verifier. So, I'm sorry, the non-deterministic machine. Let N, W, 1 to the T, such that N on W accepts within T steps. Kind of a ridiculous problem if you think about it, but that obviously sounds NP complete. It's kind of like a bounded version of the halting problem, if you think about it, which is kind of strange. So this, first off, this 1 to the T here is to make the input length the number of steps, right? Because you don't want to think about the size of the input. You want to measure the runtime as a function of the size of the input. So first off, adding this 1 to the T here makes the problem decidable. Because if you don't have that, I mean, that's basically the halting problem, which is Rice's theorem, you could throw that at it. It wouldn't be too hard. But this makes it decidable. Why? First off, let's just prove B is an NP. Why is B an NP?
There's a polynomial verifier, but
Yeah, the non-determinate, the verifier, this is a bit tricky. The verifier takes as input N, W, and 1 to the T. But it's a deterministic verifier, so let's say it takes on witness X. X is going to encode the same way we simulated a non-deterministic machine on a verifier and a verifier on a non-deterministic machine. X could encode the non-deterministic choices. So it just simulates N deterministically and up to a counter of T, and if it doesn't accept by that point, just reject. I mean, that's the definition. It doesn't need to halt, or if it's past T steps, then either it doesn't halt, or it accepts too late, or it rejects too late. Something like this, right? So that's not too hard to show, and we agree that B is an NP, right? In fact, just kind of trivially, it may surprise you that B is NP complete, right? Now I claim, well, we've proven B is an NP, let's prove B is NP hard. How do we prove for all A and NP? For all A and NP, there's a polynomial time production from A to B. This is not too difficult. What we're going to do is simply we want a reduction such that W is in A, if and only if F of W is in B, right? So here's what our reduction is going to do. Since A is an NP, there is NTM, we'll call it N, and polynomial N to the K, such that N on W accepts in N to the K steps, right? That's the definition of a problem being an NP. So our reduction is simply going to output that machine concatenated with W, concatenated with 1 to the N to the K. what does the reduction do here? It takes as input W, it concatenates the program to the beginning of it. Let's call that f of A. It concatenates the program to the beginning of it. Then it concatenates a padding towards the end of it. Concatenating the program to the beginning takes constant-ish time. Concatenating a polynomial size padding towards the ends of it takes polynomial time. So this is a polynomial time reduction that runs in polynomial time. So obviously it works. It's obviously correct, right? That's just, I mean, the definition of W is an A. We're done, okay? And notice you can do this for any A. So each A has a reduction, a different reduction, but each A has a reduction to B. So from all A, we can go to B. Questions on this one? Yes.
So I know we've gone over the non-determinism of the witness X before, but I'm just curious, not why it works here, but to give me a better sense of when it wouldn't work, like when you can't just throw X as a witness, or that might be a tangent.
What do you mean you can't throw X as a witness here?
So here we have to encode the non-determinism, but are there any cases where the problem, we can't just encode the non-deterministic,
Yes. The witness must be polynomial size as well. So if the witness is exponential size in any sense, or there is not a correct encoding of the witness in polynomial size, then it probably wouldn't work, right? So there are problems that are verifiable if you unbound the witness. In fact, if you unbound the witness size, it's a recognizable languages. That's actually a homework problem. You can decide halt with such a verifier. But it needs to be, by the definition of NP, we want it to be a short, convincing answer or proof. We want it to be like a terse, efficient thing, right? So not every problem has an answer, but not every problem has a short answer. So that's when it would be. And sometimes you'll see in a paper that they prove something to be NP hard, but they cannot sufficiently prove it to be NP complete because they can't figure out an encoding of it in NP. They can't figure out the witness, basically. And it turns out then some papers pass, there is no witness, it turns out, something like this.
so X couldn't be countably infinite?
Oh, no, yeah, these are strings. Yes, certainly, finite strings. And it's better to think about programming, like everything is just code. Right? Okay, so we've proven that B is NP complete, and now we have a singular problem. We could just stop there and say that there's an NP complete problem. But we want to prove a combinatorial problem. All these combinatorial problems are NP hard, which comes from SAT. So in fact, now what we want to do is prove there's a polynomial time reduction from B to SAT. So what we're going to do is we want the reduction to take on input n, w, and 1 to the t, which is the time bound, and we want it to output a formula phi, which has quote-unquote hard-coded m, w, and t in it. And it takes on some x, okay? We want it to output a formula, given the machine word time input, okay? So what are we gonna do here is this CNF is going to quote-unquote simulate the machine on the word. A formula cannot simulate anything. It's a static object, it's got ands and ors in it. But it's effectively going to simulate n on w. And we will design the formula in such a way such that it is satisfiable if and only if the machine accepted within the time bound. The way it's going to work, though, is that this formula will have a bunch of variables. The satisfying assignment to the formula will either be two things, depending on which proof you do. It'll either be the non-deterministic choices, or it's just going to be the witness. If you do the verifier definition, this is going to be a formula that takes as input an encoding of the witness and pretends it's the machine executing on the witness, and then it outputs a 1. This formula will be satisfiable if that machine was supposed to accept, right? That's kind of what we're doing. This may not be so surprising because it's basically taking a program and converting it into a circuit. But this is not a circuit necessarily, it's a CNF, which is slightly different than a circuit. We'll talk about circuit level programming in a second. Any questions on the high level? Okay, before we get into the nitty-gritty, one more quick sentence. To prove SAT is NP complete, we need to, I'm jumping ahead. We need to first prove it's an NP, and then we need to prove it's NP hard. So that's the NP hard argument. Why is SAT an NP?
Because you can plug in a candidate solution and evaluate it on no time.
QED. SAT is an NP. Why? The verifier on input A, C, and F, and witness X plugs and chugs X into phi, right? There's some more that needs to be said here, but not really. Like, first it checks that phi is of the correct form, it's a C and F, there's no misplaced ands and nots and whatever, and then it checks that X is exactly the number of input variables, bitwise, and then it assigns them in there, and then it can plug and chug, right? So whatever, no, without making too many specific data structure decisions, like how is the formula given? Is it a structured object? Is it a string? Whatever. Doesn't really matter. All those matter up to polynomialness, right? So that's efficient for us to show that SAT is an NP. So at least, SAT is at least easy in the sense that it can be verified efficiently. It's not something worse. Now we need to show SAT is NP hard. Before we do this, let's describe something called the tableau construction. A tableau is just a fancy word for table. But basically what we're going to do is create a structure that is going to help us with the formula. So consider a Turing machine of this form. Right? The tableau for this machine, let this be Q0, QH. This is not a non-deterministic machine or by any stretch, but the tableau is a sequence of configurations organized into a table. So let's consider the first configuration, Q0, 1, 1, 1. Let's give it a blank. Okay? What's the next configuration going to be?
Zero, Q0.
Correct. The next one will then be 0, 0, Q0. And the last configuration, just because I said left, we'll do that. Okay. This is the tableau, okay? It's just a table. And the table is basically, we're going to convert the computation of the machine into a table like this, and then convert the table into a formula. In some sense, the formula, the table doesn't exist. It's just like a mental thing. But the table, the formula, all it needs to do to simulate the machine is check the table. So the table could be provided as input to the CNF through a sequence of variable encodings. The formula is simply going to check the table, right? It's going to have to check a few things. But you can determine if the machine accepts if this table satisfies a few simple checks. So the core idea behind Cook-Levin, there's like 13 books that claim to cover Cook-Levin, okay? There's like 3 of them that actually do the proof in detail that we're going to do today. A lot of them say, well, the computation can be determined by the and of many checks, and that's a CNF, so we're good to go. But we're going to go in a little more detail about that. You can forgive them for not wanting to do so because it's basically a lot of programming. Imagine you had and, or, and not gates as a programming language. That's basically what we're going to do today. We're going to rewrite a non-deterministic machine into this and, or, and not gate language. If you're familiar with circuits, that doesn't sound impossible, but it just sounds tedious, which it actually is. But this can be determined to be correct by a few simple checks, okay? The checks are as follows. The formula will be the and of 4 checks. Something called phi cell, phi start, phi move, and phi accept. Okay. Cook's original proof, by the way, was like 8 checks, and he actually showed a different problem, was co-NP complete. This is something horrible. But this is the simplest proof that we have today. These 4 checks are going to be sufficient for us to determine if the machine accepts. And we'll create CNFs for each of these parts. Notice that because they're ANDed together, if you AND CNFs, you get another CNF. So this is going to be some CNF, right? Phi cell is simply going to check that exactly one symbol is in each cell. Phi start is going to check the first line is the initial configuration. Phi move is going to check that the next line follows from the previous line, right? And then phi accept is going to check if the last line accepts, okay? Pop quiz, what is the depth of this tableau? Don't say 5. As a function of the machine. For any Turing machine, for any tableau, how big should the table be, essentially?
Size of the input?
Almost. Here it happens to be the size of the input because we have a linear time machine. The depth of the machine will actually correspond to the time. So this first line, imagine it not only has the input, but it also has the, if you want to do it for the verifier, it has also the witness. So computing on the witness could take polynomial time. Or we can just think this is a non-deterministic transition function. Let's do the non-determinism one, okay? This is a non-deterministic machine, so this runs in some polynomial, okay? What's the width of the machine? You might think it's the size of the input, but it could be more. It's in fact the space. But because we have a polynomial time machine, it can use almost polynomial space. So it's a poly by poly table. This is necessary for us to argue that the formula will be polynomial size. We want the reduction to take polynomial time. So we have to argue that the CNF that it writes down must be polynomial size as well. Okay? So let's just get started into the construction. What are our variables going to be? Let xi, j, s mean cell I comma j contains the symbol s, where s is a letter, right? It could be q0, it could be a blank, it could be a hash, it could be a 1, something like this. So we're going to have variables for all I, j, and s, okay? We want to construct a formula as a function of these variables such that it has the properties that we want, right? So let's do the easy one first. How can we do phi start? Phi start should be something that confirms that the first line is exactly what we think it is. Yes?
The first line of the table?
Yes?
Okay.
We want to confirm that the first line of the table is exactly the initial configuration. It's almost too simple, which is why it feels like a trap.
Make sure that Q is starting on the left, all the way to the left, or...
Yeah, I think you understand it. You wanted to check it's that exact string. So what we do is we'll say, let this be x1, 1, hash, and x1, 2, q0, and x1, 2, w1, and dot, dot, dot. And we're gonna get, what is this? And x1, n plus 2, wn, and x1, n plus 3, blank, and some more blanks. We'll call this and x1, what is this? N space plus 1 blank and x1, n to the s plus 2, hash. Something like this, where the dimension is n to the s, right? So let's call this n to the s plus 2. 2 for the blanks, and n to the s is the polynomial amount of space, right? Okay, would you agree that if these variables are all set to true, then the first line is exactly as it should be for the way we define the variables? Okay, what about, this one's simple as well. What about phi accept?
last line of the table matches the accepting state?
Correct. But one of the problems with Cook-Levin, lots of little programming details. So high level, that's exactly what happens, but we need to be more specific, unfortunately. The machine accepts if there's an accepting configuration. So what we do instead of, we could just search for the last line if there's an accepting configuration. But instead, just to make things simpler, we're gonna just loop over the entire table. So we're gonna make one clause of polynomial size. So it's gonna say an OR of 1 less than equal to I less than equal to n to the t, and let this be n to the t. 1 less than equal to j less than equal to n to the s. If any of these are an accepting state, any symbol in this table is an accepting state, we accept. Sorry, this formula will be satisfiable. I, j, q, a. There we go. Now, will that come on the last line? Absolutely. Okay. So we've done 2 of the 4 parts, right? We've done accept and we've done start. We now need to do cell. Cell is going to just ensure that the variables can be whatever they want, right? We just need to ensure the variables correspond to the table. So we need to ensure that exactly one symbol is in each cell of the table, and not 2 and not 0, right? The table isn't real, the formula is real. So we need to have the correspondence between them be exact. So we say phi cell will be equal to, we want it to be the case that none of them are off. For each ij, at least one of them is on, and that not 2 of them are on, right? So I'll just tell you what this one is going to look like. This one's a bit more complicated. We want something to be true for all I less than equal to 1 less than equal to n to the t, 1 less than equal to j less than equal to n to the s. So we're going to loop over the entire table, okay? And then we do some checks on each cell of the table. First, we ensure that for all that a symbol is on for xi, j, comma s. At least some of them is on. Where c is equal to, let's say, what did I say this was? Q or hash or a tape symbol, right? So we say check for each symbol, for each i and j, at least one of the symbols is on. Do we agree this ensures at least one symbol is on for each one? So for example, I equals 2, j equals 3, none of them are off. If this formula is satisfiable, this must be on, right? And we want to ensure that no 2 are on at the same time. So it couldn't be the case that ij q0, ij hash are all both on. Like 1, 1 hash and 1, 1 blank are both set to true. We want exactly one symbol in each cell. So what we're going to do is ensure that no 2 are on. So we'll call this the AND. S comma t in C, such that S does not equal t, of xi j s is false, or xi j t is false. Okay. Now that's not exactly a CNF as we know it, but you could probably unfold it a little and creatively think that that is a CNF. Okay. This first part just checks that at least 0 of them are on, more than 0 of them are on, and less than 2 of them are on, right? Yes?
When you say on, you mean in the cell?
So we don't know what the satisfying assignment is to the CNF, but we want it to be the case. If there's a satisfying assignment, the machine had to accept. We want to make this if and only if correspondence without actually knowing if the machine accepted or not. So someone else, we're going to write down a formula such that if someone else were to walk by and plug and chug into it, they knew if the machine accepted. That's the only way they could satisfy the formula. So we'll make it so, this is more of a structure thing than anything about the machine, but we want the encoding of the variables to actually be an encoding of the machine, right? The computation history of the machine. They're going to actually decide what symbols go where, right? What the formula does is just check, this is the input in some sense that the person, God or whatever, is providing. And the CNF simply checks this information, right? So we want to ensure that it actually does look like a table. So we just check that no two symbols are in the same cell and every cell is filled in. There's no blanks, right? But this table is in some sense the input to the CNF, okay? But we have to make sure some data structure things go around it, okay? So do we agree though that that formula ensures that exactly one is in each? It's a little bit of a difficult programming thing there, okay? Okay, now we need to do phi move. Phi move is the most difficult one. Essentially, if you think about computation, we need the CNFs to be kind of small. So how do you determine that, what we want phi move to be is that, in English, is like if row I is ith configuration, then row I plus 1 is I plus 1th config Ci plus 1 such that Ci yields Ci plus 1. So in some sense, the ith configuration, the phi move is supposed to be kind of like an inductive hypothesis, right? So phi start is kind of like a base case. Phi move is kind of like an induction step, where like, okay, phi start ensures for us that the first line is correct. Good. Phi move ensures that if the ith line is correct, then the ith plus 1 line is correct. But since the first line is correct, then the second line must be correct. And then since the second line is correct, the third line must be correct. And since the third line is correct, the next line must be correct, right? Now the problem is, how do we check that the next line is correct given the previous line is correct? That's kind of difficult to do, but what we can do is associate cells from one row to the next, right? So if we know one row, in fact, we can determine what the next row could be, right? In fact, by non-determinism, if you know what a configuration is, you actually know what the next possible configurations are by the transition function. So the way you can actually compute the next line from the previous one is simple. It's just look locally. What is the difference between the top row and the next row?
The first two cells.
Everything else is the same. So in fact, what this phi move is going to do is check these 2x3 windows, okay? Everything else is going to be identical. But notice that the computation is very local, and that per configuration to configuration, the only thing that really changes is a very small portion. If the input here we only did 1, 1, 1, but imagine we did 1,000 ones or something, right? Only a small part gets changed in each next line. So if you notice the tape head, the tape head only gets changed at a very small portion of it, right? So what we're gonna do for phi cell is ensure that every 2x3 window is legal, right? And then what a legal window is can be enumerated. So what are some examples of legal windows? A legal window, let's say we have, I don't know, QI, read A, write B, move left. Sorry. A legal window could be like A, QI, B. What is that? B, QJ, something like that, right? That's an example of a legal window. Another example of a legal window could be, you know, A, B, C. Let's say A, B blank, A, B blank. So how many legal windows are there for any Turing machine? I'm not looking for a complex answer. I'm looking for a really simple answer.
The number of combinations there.
I'll tell you the simpler answer, finitely many.
Uh,
Convince yourself, in fact, up to non-determinism, there are finitely many legal windows. There are a lot more illegal windows, but there are finitely many legal ones, right? So all phi move is going to do is double for loop over each 2x3 window, and there might be some minus ones and stuff necessary here. Let me see. 1 less than equal to I, less than equal to n to the t. 1 less than equal to j, less than equal to n to the s. And then we're gonna ensure that window I comma j is legal. So how do you determine that the window at ij is legal? What you do is you just check that those 6 values are from a specific hard-coded list. So the way you'll do that is you'll say, x, let's say I, j minus 1, a1, what is this, and x, I plus 1, j plus 1, a6. There we go. Now that could be rewritten as a CNF, although it's not a CNF as is. You have to be careful when you make arguments like that, and I'm being a little lazy. Sometimes when you rewrite a thing into CNF, it could have, for example, exponential blow up. That's not the case here though, right? And we want a polynomial size CNF. But this is a CNF that checks if for every window, the windows are legal size, right? Okay, so the reduction takes as input the non-deterministic machine, the word W, and the time bound. Using the time bound, it can determine the size of the table, and then doing so, it can construct these 4 parts and AND them together. So the reduction will actually take the machine and write down these 4 parts. This could be done in polynomial time if the size of the formula is polynomial size, right? So we need to kind of argue, before we get to the argument about the correctness of the reduction, are there any questions about the phi move portion? Do we agree that this English sentence is satisfied if we can determine these 2x3 window argument, right? The and of many small checks ends up giving you the thing. That's kind of the core idea behind Cook-Levin. It's like determining if a machine accepts can be encoded into a CNF. It is the and of many small checks. These are very small checks, six checks. Just and a bunch of those together. That's your CNF. It's a big CNF, but it's still polynomial size. So that's good enough for SAT to be universal in some sense, right? Okay, we need to argue about the size of these formulas. Phi cell is approximately how big? Here's phi cell. Well, you can think of this like a double for loop. And then in here might be like another double for loop. Nope, that's not a double for loop, that's over symbols, which there's finally many of them. So this is approximately a double for loop, right? So what's the size of this formula?
Would it be t times s?
Let me think.
N to the t times n to the s.
Yes, so that's approximately O of n to the, well, I'll make something, just to make the formula, so that's perfect and that's correct. But to make something simpler, what is the relationship between n to the t and n to the s? If a machine takes a certain number of steps, it cannot use more space than that, because each new cell it uses must use a unit of time, right? It can always use less space than time. So, in fact, we know that n to the s is less than or equal to n to the t. Not even big O-wise, just like literally the number, right? So in fact, we could call this, you would say n to the s plus t, which is correct. But let's just simplify things and call this n to the 2t. Okay? Just so it's obvious it's polynomial in one variable, right? The size of phi start is what?
I guess it would be the size of the first line, so it would be s.
Yeah. N to the s, which is less than t, so let's just upper bound that by O of n to the t. It is this, and s is the, I'm using it, this is a bit bad habit of mine, but I'm not using it as the space, but n to the s is the space, so it's a polynomial, right? about phi, what do we got left? We got phi except. How big is phi except?
Also n to the t? Oh, no, because it goes through the whole thing.
It's a double for loop, so we call it 2t.
N to the t.
What about phi move? This is the hard one, the ugly one. But in some sense, the most important, right?
N to the 4t?
I actually don't know. Let's see. This is a double for loop. The window, checking the window ij is legal. This whole thing should be a constant. There's constantly many legal windows. There's 6 things to check per window. So this is something big, but it's a constant for each one. So this is 2c. Okay? So the size of the total formula, which is the and of those parts, is just O of n to the 2t. So this polynomial time reduction can write down this polynomial size formula efficiently, right? Now, it doesn't know if the machine accepts, but it can write down the reduction. That's kind of the core idea. I have a lot of comments on this proof. First off, Cook-Levin is tedious and ugly and a bit annoying, but it's very important because unless you, and this is the read, now that we can see the proof, you maybe have some humility about why we don't do this in 3510, okay? We need a very formal model of computation in the Turing machine in order to even do this. It's easy to just kind of like wave our hands around, like SAT is probably hard, right? But this shows that all of n can be reduced to SAT. And then from SAT you can reduce to 3 SAT. Question? Yes.
Did you check the 2 lines outside of the window stays the same?
That can be done through the legal window stuff. You check that hashes only appear.
I see. Okay.
The hashes also are not even 100,000% necessary. They're just there to help some of the legal window
So
stuff.
the legal window stuff is not just around the tape head.
Correct. Oh, no, correct. And in fact, there are many copy legal windows, like this one, that are there for every single thing. For all possible 2x3 legal windows. Yeah. So it's not important that you know this proof to heart, but it is important that you could be convince yourself that it's correct. Because many times in complexity theory, we will use this sentence that's something like, by a similar argument to the Cook-Levin theorem, there exists a CNF for blah, 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 blah. We could program a CNF, but we don't want to. So just convince yourself that you could program a CNF. We may need a CNF with a certain property in the future, and we say, oh, we program a CNF that has a certain thing. If this machine accepts, this CNF will do this thing. We can make such CNFs. Yes?
Well, would I also have to guess n to the t?
No, because
Instruction.
technically in the reduction, the machine knows the time bound because it's given.
I see.
Yes. So the reduction knows the t, and that thankfully it does. If it didn't know that, this would be very difficult. You'd have to guess for every such t, there's a different reduction, something like this. Right. What else? So it's important you understand Cook-Levin conceptually, so you can like make generalizations in the future without having to think too hard about it, right? And so now that we can go from SAT, we have gotten to a CNF, you can now actually go then to 3 SAT, and then to independent set and Mario and subset sum and all these other things. They all, and again, I want to emphasize, this CNF, we don't know if it's satisfiable or not. We were able to compute the reduction without knowing if the machine actually accepted or not. Because such a thing is thought to be not in polynomial time solvable, right? But if you were to do this reduction for a verifier, a deterministic verifier, you would have less legal windows and some other small changes, but the input to the CNF would literally be the witness. The witness would take as input to the variables. Here, in some sense, the witness is the computation history of the non-deterministic machine. So if someone knows if the machine accepts, they can convince you of it because they have the history of the machine, which is the witness in some sense. Sorry, which is the satisfying assignment, right? I'll give you one more proof of Cook-Levin, which is like I don't want to say it's the better way, but it's the more algorithm way.
So, real quick, phi
Yes.
proves that SAT is NP hard.
This proves that, so we did that little language B over there. we went from every language to B, and then we went from B to SAT. So in fact, every problem can be reduced to SAT because you can encode a formula that is satisfiable if and only if the non-deterministic machine accepts. So the complexity of all of NP can be reduced to the complexity of a single problem. It's like an unelected representative in some sense.
So it's proving that, okay, so it's proving that, not that, okay.
Yeah. So CLRS, you may be familiar, is an algorithms textbook. It's more like an encyclopedia. 1,300 pages, very tedious. It's as thick as a phone book. You can sit on it. And they have a whole chapter on NP completeness, but they focus on reductions and not necessarily on Turing machine computational models. So they outline the Cook-Levin theorem in this way. So this is their proof that circuit SAT is NP hard, right? So what they do is they say circuit, we're not going to do CNF SAT, we're going to do circuit SAT. That's the first difference they do. And what they do is they argue that, okay, suppose you have a polytime verifier. You have a verifier, and let's suppose it's not a Turing machine. We have then a sequence of configurations of this actual machine. And the actual machine is like a RAM register machine, okay? So they say, align the configurations in such a way, okay? And then let each configuration be all the information about the machine. So it contains the auxiliary machine state, it takes PC, I don't know what that is, but there's a program description, there's the input X and the witness Y, and then there's some storage, there's some registers. Each of these can be encoded as polynomially many configurations, okay? Then they argue kind of loosely, you can create this circuit M, which takes as input one configuration and will always output the next. Such a configuration is constant depth. You perhaps believe you could do it with Boolean programming. You've done enough circuit work in 2110 that you believe you could do it, even if you don't want to. It's probably possible, okay? Slap that together, that's a circuit, okay? Polynomial depth, because it's polynomial time. Polynomial width, because it's polynomial space. Polynomial by polynomial, this whole thing is just a giant polynomial circuit. You have a single output wire for the 1 or a 0, whether or not this witness is, and the input to the circuit, by the way, is only this Y. Everything else is hard-coded, it's only this Y is the input to the circuit, and the output's a 0 or 1. So this is high level, kind of the same thing. But CLRS, they don't have like a formal model of computation. At least I don't think so. They would not talk about a Turing machine, but because they're an algorithms-focused book. But you can still, it's the same idea. Like, and many books talk about Cook-Levin in this like high level, like, here's kind of what would happen. Let's not talk about the details, right? The M, for example, is not really specified, but everyone can be convinced this could be done, right? I just wanted to show you some of the details. Oh, one last thing I can say about Cook and Levin. Cook, famously, the story is, he came up with the Cook-Levin theorem in 1971, and the same time he defined the P versus NP problem. And he famously was denied a job at Berkeley for some reason, I don't know. They were like, we don't want to think about this stuff too much. And then he immediately went to Toronto, immediately proved the Cook-Levin theorem. And then like, they were like upset that they didn't get to keep him. Something like this happened, there's some famous story. Levin was actually a PhD student under Kolmogorov, as we know, and he was working on many problems that were not very combinatorics focused, but like brute force search focused. The Russians were trying to prove that some problems were, it was called parabor, which means like inherently the only solution is brute force search. It's in a cybernetics kind of perspective. And he was able to prove not only the Cook-Levin theorem, but all these, he proved not SAT was NP complete, but a tiling problem was NP complete. And all these other problems about, that CARP had to prove, which were, you know, clique and scheduling and all these other coloring, these were all NP complete as well. So he proved those in a different way. And then I think Levin had to leave for some political issue. He came to the States. He had a very long established career. He did a lot of good work. What else? Yeah, it's interesting that Cook came up with a logical problem because he was a classically trained logician under Hao Wang at Harvard, who was doing problems kind of like PCP. And if you think about it, what difference is there between this problem and the PCP problem? Not too much reduction-wise. It's kind of similar, right? So you can kind of see the history about where that comes from. Any questions?
What's PCP again?
Remember the post-correspondence problem, the tiles?
Oh.
Yes. The tile set encodes the machine computation history.
Yes, yes.
We have CNF encoded machine computation history in some sense. But the difference is that encodes even a machine that may be stuck in an infinite loop. This encodes a non-deterministic machine that still always halts. Slight differences there, but you can see inspiration, prior work. Complexity theory is simply building upon computability theory, really. That's what the moral is. All right, let's take a break. Question? Okay.